Okay. Hello, everybody. Today I'm going to be finishing up with 6.4. We're really kind of already done with it, but I wanted to run a couple more examples. And also talking about 6.5, which will very much seem like section 5.4, where we talked about inverse trig functions, but we will also go into their graphs today in section 6.5. So I'm going to go ahead and jump into, I'll just call this 6.4 continued, just get a couple more examples here for these graphs, right? Because we're learning new graphs, right? The 6 new graphs, sine, cosine, tangent, cotangent, cosecant, and secant. And also recalling all those transformation rules. All those transformation rules that we had from 112 and how they can be applied to these graphs. Okay, so let's look at what problems did I give you. Let's see, 6.4, number 4, and 35. Let me pull those up in the text real quick. There. So number 4, secant of 2x, already talked about that. And then 34, no, that's not right. 35, nope. Oh, I'm looking at the wrong section. Okay, number 6 and 10. So let me look at number 6, negative tangent of x. So let's say I have a function equal to negative tangent x. What is number 10? Sure. I'll leave number 10 for you. So this is number 6 from the review problems that I gave for this section. All right, so what do I need to know here? I need to know what the base graph of tangent looks like. So if I draw tangent, I know that it has period of pi, right? It has a period of pi. So unlike sine, cosine, secant, and cosecant, which all have periods 2 pi, tangent and cotangent have period pi. And also a weird thing about tangent is that a natural interval to draw it on is not just from 0 to pi like you would expect, but instead from negative half pi to negative half pi to just a regular half pi. So negative pi on 2. So this is negative pi on 2 right there to pi on 2. And why am I drawing these dashed lines? Because tangent has asymptotes, right? Asymptotes, which was kind of the theme for all 4 trig functions, excluding sine and cosine. They all had asymptotes, right? But tangent acted a little bit differently because it does this thing where it starts at 0, 0, and it almost looks like a cubic function, sort of, except a cubic function doesn't have asymptotes. And the tangent function will go like this. Excuse me, and we'll come down this way. And I walked through the construction of the tangent function. It should be symmetric here, should be a little bit more curved here. I walked through the construction of the tangent function in last lecture, so I'm not going to go through like why it looks like this. And also note that it does repeat this shape, right? It repeats this shape for every pi. So the next asymptote out this way would be at 3 pi on 2, right? Because that's if I increase by pi, that's what I'm going to get here. And it would be like this, etc. And it would go the opposite way as well. Just a whole bunch of these crazy shapes. Now, what I want to graph is negative tangent of x, right? And does it say you're just matching in the actual homework problem, you're just matching. But if you were actually asked to sketch this, you would probably just be asked to sketch 1 period of it. Instead, this is 2 periods of it that I've drawn here, but you would probably only be asked to graph 1 period of it. Sometimes I graph more than 1 just for clarity. And if I'm only graphing 1, I don't need this massive x-axis, but oh well. Okay, so I want to negate the outside of the function. So this is just tangent x, right? This is not what I was asked to graph. This is f of x equals tangent x, right? That's the base graph. Now I've negated it on the outside. That means that I've given it an x-axis reflection, an x-axis reflection. So I'm going to have the same asymptotes. It's not like shifting or anything or stretched or compressed. If it's not shifted or stretched or compressed, then you're going to have those same asymptotes. And I'm just going to flip it over. I mean, that's all I'm going to do. I'm going to flip it over the x-axis. So it's going to look more like this. That would be one period of this graph. F of x equals negative tangent of x. And in these particular problems, you're just asked to, like, literally this is number 6 in section 6.4 from the text, and you're just asked to match it. You're asked to match it to one of these graphs. And it would be, you won't be able to see this. These are the choices you get to choose from. 6 choices here. Clearly it would be this one here. And I've also given you number 10 to do, and I will leave that to you. So I just wanted to do at least one more example from this with a transformed tangent function. Okay. So now let's get into 6.5. So understand that with the 6.3 and 6.4, I can't graph every single combination, right? So you're going to have to do some extra work, homework exercises, and playing with Desmos to see what the different graphs look like. Because I can graph each of the 6 trig functions for you, and I have. But as far as like getting every different type of transformation, right? I'm kind of leaving some of that studying to be done outside of class, just because it would take, a whole nother week to go over every single kind of transformation in detail. All right, so let's look at inverse trig functions and their graphs. 6.5. All right. If we have a trig, function defined via the unit circle approach, so if I have like cosine of some arc t, so this is on the unit circle, this is some arc t subtended by some angle t, and then concluding at some point xy, then literally cosine of t yields that x value, and sine of t yields the y value. Then I know from our discussions in section 5.4 that if I'm actually given the point, like in this case, given the x coordinate of the point, then I can invert the trig function and say, well, if I'm looking for the arc length or the angle subtended by the arc, then t can be equal to cosine inverse of x. And similarly, down here, t can be equal to sine inverse of y. Okay, so this is like just unpacking. In this notation, what's going on is it's just an inverse function notation. That little -1 means like inverse function notation. So what we're doing is we're going from given some coordinate point data, like some coordinate point, literally like an x coordinate or a y coordinate, and also we'll be given data about what quadrant we're in. We'll have to be given that as well. Then we can find the arc length or angle subtended by whatever that, or rather where that terminal point is. Okay, so what else did we have to say about the inverse functions in section 5.4? We had to discuss their domains and ranges, and I made a big show of that, right? I went on like a long discussion about that, so I'm not going to open all that back up, but I will kind of write down the conclusions, which were that the domain of the inverse sine function. Hang on. In between from here to here, I'm making the change. I'm going to go ahead and switch back to their notation. So let me make a note here. Switching to book notation and book and WebAssign and all that notation, where for any function, they're letting x be the input. So like, I'm gonna just say this on a different piece of paper here. Switching to book notation, they'll say cosine of x. How do they say it? Hang on. Let me see how they, because I went and looked specifically at the problems in WebAssign that they're giving you. They say if cosine of y is equal to x, then that means that y is equal to cosine inverse of x. Has nothing to do with the x and y coordinates up here, which is unfortunate. And if they give you sine of y is equal to x, then y is equal to sine inverse of x. So they're just, again, the point they're making is that the result is we're talking about these inverse trig functions. So they want x to be the domain variable for those inverse trig functions. That's why they set it up like this with y in the original input here. It's dumb. I'm not even gonna lie to you. It's just like, the more I think about it and the more I talk to like other professors, well, I'm not a professor, I'm just an instructor, but actual professors who have their PhDs and everything, they agree that this is just dumb. Because the whole point is this picture right here. We should always be able to come back to this picture, and this just completely throws a wrench in that because they're not the same x and y. All right, so let me get off my soapbox and say the domain of sine inverse of x is -1 to 1, okay? And the range of sine inverse of x is, the range has to be restricted, right? The range has to be restricted, and we already talked about all that. So I'm just going to go ahead and write down what we decided we needed to restrict the range to. I would say that it would not hurt at all to go back through section 5.4 and watch that video, or videos maybe, for section 5.4, because that's where we built up all this stuff about domains and ranges. But it's going to be a bit more meaningful here, at least, because we're going to get to see pictures. Okay, so the domain of cosine inverse is the same as the domain of sine inverse. No problem there, -1 to 1. And the range we restrict. So the interval size of both of these ranges is just pi, right? -½ pi to ½ pi. And this one is 0 to pi. They're just on different parts of the number line. Okay, so we've restricted the ranges of both of these functions. Okay. So let's talk about how we use these sine inverse and cosine inverse functions. And by the way, are we going to talk about inverses of other functions? We'll talk about inverse tangent, but we're not really going to get into inverse cosecant and secant and cotangent. We could, but it's just not time. That would kind of be an extra thing. All right. So how do we interpret? How do we interpret sine inverse of, say, square root of 3? No, let's see. Sine inverse of, yeah, square root of 3 over 2. Like, literally, how do we solve this? How do we interpret what it's asking? This is asking for some angle, right? This is asking for an angle. The output of a sine inverse function should be an angle. Like this in the end will equal some angle, probably in radians, right? This is asking for some angle that let me say this first, that falls in the range. What is the range of sine inverse? Negative pi on 2 to pi on 2. So first of all, that has to be satisfied. That solves this equation. So what else? It also has to solve the, is my grammar right? That solves the equation. What is the equation that we're trying to answer here? Sine of some angle. Oh, what letter do I use without making the book mad? I'm just going to say t here because it could, yeah, that's fine. Square root of 3 over 2. That solves this. There's some angle exists so that when you plug it into the sine function, it gives you a y value out that is square root of 3 over 2. And there are many angles that do this, actually. There are infinitely many, right, that do this. But there's only going to be one in this range, ideally. Okay. Well, no, there will only be one in the range because that's why we constructed it to be this way. If sine inverse is supposed to be a function, then one input should not go to two outputs, right? Because that fails the definition of a function. So there will only be one answer in this range. And what is it? So we have to have our reference triangles. Like we got to be like real good with these. You know, we've been doing them the whole semester, so hopefully this is like becoming more comfortable at this point. That you know it should be either like a pi on 6 or a pi on 3. Right, just based off of like this number here, square root of 3 over 2, we're thinking either like some pi on 6 triangle, which would have square root of 3, 1, and 2. So my sine output here, sine of pi on 6 is going to be 1 over 2. So that's not it. If I flip it to be a pi on 3, there's pi on 3 in there. And now this is 1, that's square root of 3, and that's 2. Basically just kind of turning this triangle around, right? Then now sine of pi on 3 is equal to square root of 3 over 2. So my answer is pi on 3, but I also need to make sure that pi on 3 falls in this range, and it does. So what I'll say is since sine of pi on 3 equals square root of 3 over 2, and pi on 3 is in that where it's supposed to be outputted, right? Pi on 3 is in there because it's less than pi on 2, right? So since it's there and there, we have sine inverse of that coordinate point, that y value of the coordinate point, that y value, the sine inverse function is going to spit out that angle pi on 3. Okay. So let's see what's next. Let's look at a cosine one. How do we interpret, say, cosine inverse of square root of 3 over 2? Oh, real quick, I need to tell y'all something. You may see cosine inverse and sine inverse written as arc sine and arc cosine. Sine inverse of x can be written as, so I believe originally when people built these trig inverse functions, which I forget who is given credit for creating them, they they very much did rely on the picture that I keep drawing. And they said that, well, the inverse functions are outputting an arc on the unit circle, right? An arc, literally where the angle, they're outputting an angle, but on the unit circle, the angle is equal to the arc. So they didn't call them sine inverse and cosine inverse and tangent inverse. They called them arc functions. So it can be written as arc sine of x. And similarly, cosine inverse can be written as arc cosine. So, oh, I forgot the word as, can be written as arc cosine. So what is this about? Why did we make the change to cosine inverse, sine inverse with the little -1 there? Well, because in general in math, a little superscript -1 means inverse. It can mean multiplicative inverse, or it can mean functional inverse. It can even, well, yeah, it can mean those things. It means like inverse. So when we started working more with sine and cosine and their inverse functions more like analytically instead of geometrically, then I'm assuming that it just became more natural to start talking about them in this form. But anyways, you should know that they can be written in either form there. All right, so what were we doing? Got a little off track there. We are asking, how do we interpret cosine inverse of square root of 3/2? We're looking for some angle. Let me say, this is asking for an angle. Angle that falls in the range. Now it's a different range. Falls in the range 0 to pi, because that's the range of cosine inverse, that also solves the equation cosine of t is equal to square root of 3/2. Now from our earlier picture with the reference triangles, we actually know that cosine of pi on 6 is going to give us 1/2, but no, it's not. What am I saying? Cosine of pi on 6 is adjacent over hypotenuse, so that gives us square root of 3/2. So the angle we're looking for is pi on 6. So that means that we're looking for, so I'm just going to kind of speed this up a bit. Cosine inverse of square root of 3/2 then would be pi on 6, because cosine of, why? Because cosine of pi on 6 is equal to square root of 3/2, and moreover, pi on 6 is in that range 0 to pi. Oh, sorry, that little symbol means, you may not be familiar with that. Let me say, I'll say it in words here, is in 0 to pi. Okay, so I keep making this big deal out of like that it needs to be in the range. Why is that a big deal? Well, consider this. Consider that cosine of 11 pi on 6 also equals square root of 3/2. And if you don't believe me, you can whip out the unit circle and confirm. But it does. Cosine of 11 pi over 6 equals square root of 3/2. But we only, wait, how do I want to say? Yes, we only want one output for the for this function at this value, cosine inverse of square root of 3/2, right? So if I tell you, oh yeah, this equals pi on 6, because I just showed it here, and it also equals 11 pi on 6. Well, then what I'm going to say is, well, then that's not a function, because if you give it one value, one input, square root of 3/2, and it's giving more than one output, then that's not a function. But we specifically want to be able to call these inverse trig things functions. That's why we restrict the domain. That's why this becomes so important. So what I can say from going off this statement here, This does solve the equation, but there's two things to satisfy. You must solve the equation, and you must also fall in this range. So I'm going to say, since 11 pi on 6 is not in 0 to pi, because it's too big, right? 6 pi on 6 is the, if I make these have common denominators, this is 0 to 6 pi on 6. Clearly 11 pi on 6 is too big. So since 11 pi on 6 is not in this range, it's not in that range, cosine inverse of square root of 3 over 2 does not equal 11 pi on 6 in this range, Now, remember that in section 5.4, we considered this inverse trig stuff kind of more from an equation point of view, where you can have multiple answers. But in this section, we are specifically, the name of the section is inverse trig functions, right? So we are operating in this restricted range. So in the context of this section, we cannot have this cosine inverse of any value outputting at two different angles. Wait, where is it? There it is. This and this, right? So we say this is the correct answer. Pi on 6. Okay. Let's do some practice evaluating. Example 1. How am I doing on time? Yeah. Not good. Let's make that negative. Okay. So I'm thinking of an angle where sine inverse, or rather, I'm thinking of an angle where sine of that angle yields 1/2. Any ideas? What about these reference triangles will help here, right? Where can I put them? Which one of these is going to be given the opposite over hypotenuse giving a 1/2? It's got to be this one, right? Pi on 6. Pi on 6. And is pi on 6 in that range of negative pi on 2 to pi on 2? Yes. So this one, just straight up pi on 6. No shenanigans there. It's just pi on 6. What about cosine inverse of negative square root of 2 over 2? We should recognize this as an output from a reference triangle that has pi on 4 as its interior angles. They're both pi on 4, right? Pi on 4, and this one also is pi on 4, and the sides are square root of 2, square root of 2, and 2. And I know that since this is an x value, right? Cosine inverse of some x component of a coordinate point should be equal to some angle. I know that I am in quadrant 2, right? Straight down the middle in quadrant 2, because that point there corresponds to negative square root of 2 over 2, comma square root of 2 over 2. What is that angle, by the way? That angle is a pi on 4 angle, and it's 3 pi on 4. Again, if you got your unit circle, if you've got your unit circle, then this point should be easy to find. You're looking for an x value. You're looking for an x value that looks like this input. If you like to use the unit circle for this one, you're looking for a y value that looks like this input. Now, you will find more than one. You'll find another one down here at 5 pi on 4 that also has this x value. So you'll find another one down here at 5 pi on 4, which would be negative square root of 2 over 2, comma negative square root of 2 over 2. So that x value is matching, but which one is it supposed to be? Is it 5 pi on 4 or is it 3 pi on 4? Well, we have to consider the range of cosine. The range of cosine is from 0 to pi. Or sorry, no. The range of cosine inverse, right? Cosine inverse. The range of cosine inverse is from 0 to pi, so it's got to be the 3 pi on 4 one. Okay, let's try C and D here. Sine inverse of 1. So looking at a unit circle, where is the y value equal to 1? What angle is going to be equal to 1? Well, that's going to be up on the top y-axis, where that angle is going to be 90 degrees or pi on 2. Okay, and that's in the range. Barely, right? It's right at the edge, but it is in the range of sine inverse. What about cosine inverse? So now we're looking for an x value. Looking on your unit circle, look for an x value where you get an x value for a coordinate point where the x value is 1. What angle are we at? Well, at 0, right? Right there on the x-axis. Not -1, right? -1 would be all the way on the other side. Okay. Now let's look at E and F. Sine inverse of 2. And F, cosine inverse of -3. Well, recall that the definition of sine inverse, well, no, I don't mean to say definition. I meant to say domain. Where are they? Oh. The domain of sine inverse is -1 to 1. That means the stuff that you're allowed to plug into the sine inverse function has to be in -1 to 1. This 2 is outside of that domain, hence we say undefined. Similarly, cosine inverse, its domain, the only allowable values that you can plug into this cosine inverse function are -1 to 1. -3 is outside of that domain, so we say undefined. Okay. One second. Okay. Here we go. Now, let's get into some weird examples. So I said that, this inverse function notation is useful because it kind of shows how the functions like sine and sine inverse sort of cancel each other out, right? And you may already be thinking, like you may have already noted that, oh my God, I'm so sorry. My girlfriend got a new cat. And all right, Kitty, come on. You lost your office privileges. Go on. Go on. Dang, she's snuck right up there. Okay. So we're thinking like that, does this idea hold? Sine inverse of sine of x. Ooh, I didn't mean to put that in parentheses. Sine inverse of sine of x. Does that equal x always? And similarly for cosine, does it work like that? Well, the answer is no, not always. The answer is no, not always, because of that weird issue where it can be falling outside of the range or something like that. So ideally, yes, because this is how like inverse functions should work. They should cancel each other out, and you should just, like, if you compose them, if you take the composition, then you should just get that input out, right? You should just, it like cancels out and you just get the x. But let's look at some examples where that doesn't exactly work. All right, so let's say sine inverse of sine of pi on 3. Okay, so calculating this from inside out without taking this rule, right? Because we're saying, I've already told you it doesn't always work. In this case, it actually will work, but let's see how it does. So inside out, so sine of pi on 3 is going to be square root of 3 over 2, right? Let's see, I got to imagine the reference triangle. Yeah, tall side is square root of 3 for the pi on 3 angle. So that's it, all right? And then now what I want to do is say, okay, what's sine inverse of the square root of 3 over 2? But we already did that, and you could reconstruct it and everything, but long story short, you're getting pi on 3. So this one does obey this rule. This one does obey the rule. They do just cancel each other out, and you do end up just getting the pi on 3 out. Okay, what about part B? Let's look at sine inverse of sine of 2 pi on 3. So what we're doing right now is function composition, by the way, if you remember from 112, we're composing functions. The notation you may have used in 112 is, well, you might have seen it as like f of g of x, like this. I wouldn't use that here because I would have to first define sine inverse as f and then sine as g. I would have to like name them to be able to use this, but that's what we're doing. We're plugging a function inside of another function just to see what happens. All right, so let's work this one from inside out. Let's not assume that it's going to work. I mean, it worked for the first one, but let's be careful. Sine of 2 pi on 3. That's over in the second quadrant. But it gives me the same output because in the second quadrant, the y values are still positive and sine should yield a y value, still positive. So it gets, okay, so that's what's happening here. But look, when I plug that in here, I already know this should be pi on 3. So we see that this thing yields pi on 3. It does not just pop out a 2 pi on 3. Why is that? Why is that? So here's the rule. I'm just going to go ahead and it's going to be the same or similar for cosine. So I'm going to go ahead and write down the rule. The rule is sine inverse of sine of x is equal to x only if that x value, that x angle, is in the range of sine inverse, is in negative pi on 2 to pi on 2. So it worked for part A because that pi on 3 input up here, pi on 3 is in that range. So it just popped out. It just went. You don't even have to, all this work that we did in between is not necessary. You can just write that input if the input angle is already in the range of sine inverse. If it's not, like 2 pi on 3, 2 pi on 3 is not in this range, then you've got to do the work in between to make sure you're getting the right output. All right, let's look at some similar ones with cosine, just for extra practice. Oh, you know what, tell you what, I'll go ahead and write the rule for cosine as well, since I've kind of already given away what it'll be. Oop, let me use the green marker. Cosine inverse of cosine of x will be equal to x only if x is in the range of cosine inverse, which is 0 to pi. So it's a different range. It's like the same rule, but a different range, right? Different range. Let me get some water. Okay, so C and D are going to be cosine inverse things. Cosine inverse of cosine of 11 pi on 6. Okay, that is not in the range here. So I need to do this one by hand. Well, by hand, doing all of this by hand. What I mean is I need to do it like manually, like from inside out. Can't just say, oh, equal to 11 pi on 6. Though if you're clever, then you already know that this is just going to output a very similar angle to 11 pi on 6, but just in that range of 0 to pi. We should expect pi on 6, right? But let's do it out by hand and make sure. First of all, cosine of 11 pi on 6. So looking at my unit circle, I'm looking for the x value at the angle 11 pi on 6, which I've forgotten, but we did it a second ago, but I don't need, let's see, what do I need to say? I just need to draw the angle, so it's a pi on 6 thing, and if it's pi on 6, then the long side is on the bottom. There we go. And also, I know it's positive because 11 pi on 6 is in the fourth quadrant where x is positive. You can just look at a unit circle, find this angle, look at the x value. You're going to get square root of 3 over 2. Okay, then cosine inverse of square root of 3 over 2 is equal to, well, we already calculated that earlier. That's pi on 6. Pi on 6. Okay, and that's in the range 0 to pi, so that's the solution to this one is just pi on 6. Make sure you know how to use a unit circle to go to figure this stuff out. Like if I just randomly ask you, what's sine of 3 pi on 4? You know to go find the angle 3 pi on 4 on the unit circle and look at its y value. Or if I say, what's tangent of pi on 3? Then you know to go to the angle pi on 3 and to find the ratio of y over x for tangent. Because remember, tangent involves both y and x, not just one or the other, right? So make sure you know how to do that, because I'm going to let you have a unit circle on the exam on Wednesday. I'm going to like project it on the board, or I might just have to draw it. I don't remember. But anyways, so make sure you know how to use it, how to use a unit circle. Okay, D, cosine inverse of cosine of 5 over 6. No pi values. That's a bit weird. No pi values. So what do we do here? Since there's no pi values, to do this manually inside out would be kind of difficult. Maybe we would definitely have to use a calculator, because this is not like a nice, it's not like 5 pi on 6, right? It's just 5 over 6, which is a super random like fraction, right? But I do know that 5 over 6 is definitely in that range 0 to pi. I mean, it's not one of those pi angles like pi on 2 or 3, 2 pi on 3 or whatever, but it's just some decimal number like less than 1, right? And it's definitely less than pi. It's in here. It's somewhere in this interval 0 to pi. So that means I don't need to do any work inside out to solve this. I can just say, well, since it's in that range, it obeys that rule, this rule, that it just outputs, it just falls right out if because it's in that appropriate range there. Okay. Well, there we go. All right, graphs. We need to talk about the graphs, and I'm gonna go through this. Let's see, okay. In the 112 sense, when I say 112, I mean like pre-calculus algebra. In MS 112 sense, inverse functions, if you recall, inverse functions, they literally swap domain and range, right? And sometimes you have to restrict the range, as we do with these cosine inverse and sine inverse functions. And I can also say graphically, they swap the axes. This is like a real simplification of what's going on, but it kind of, it's kind of true, right? Like an x cubed graph. If I have an x cubed graph, and I take its inverse is going to be the cube root of x, right? That's what would undo this function. And it's literally like the function on its side. It's like you swapped the x and y axes, or the horizontal and vertical axes. You literally like erase them and swap them, and it flips the function like that. So we expect then, for instance, y equals sine inverse of x to look like a sine function, but like on its side, like pointing up and down, right? So maybe like, and I'm still gonna call this side x and this side y. Okay. What do I expect a sine inverse function to look like? Well, it's like this on its side. So if I got to be careful about how I'm flipping it here. Let me actually let me get rid of this. I'm going to turn the paper sideways, and we would actually be going, even though it seems a little strange, I would be going this way, like this, and it would continue. But I know this isn't completely right because this is not a function. It fails the vertical line test. Like if I draw all the loops, it would fail it infinitely many times. But recall that we restrict the range of the sine inverse function from negative pi on 2 down here, which would hit right at that peak value right there, negative pi on 2 to pi on 2. So my sine inverse function is actually going to look like this one little wiggly thing that doesn't look like much at all, but it kind of sums up everything for the sine. It does sum up everything for the sine inverse function. I'm going to have this, that. That's the sine inverse function. That's it. If you restrict the range of sine inverse just between this little interval, negative pi on 2 to pi on 2, to make sure that it doesn't overlap on itself so that it still passes the vertical line test, this is all you're left with. That's all you're left with right there. Let me note some important values here. I've already noted some of them, but this is its top value of its range is pi on 2, and the bottom value is negative pi on 2. Right, those are its extreme y values that it can hit. And what was its domain? Its domain is from -1 to 1. So the extreme value here that it's hitting is -1. There we go. Sorry. Its domain extreme values are -1 to 1 on the input axis here. Okay. Cosine inverse is going to be similarly defined, but let me go to Desmos. You don't want to see all that. All right, Desmos. Let me just show you a sine inverse function. Is that going to do it? Yeah, there it is. See, it really is. That's seriously all it is. And we see the extreme values here happening at -1, negative pi on 2. And of course, it goes through 0, 0, and all the way to 1, pi on 2. So restricting it is ensuring that it is still a function, because if I went any further and it started to loop back down, then it would start to fail the vertical line test for functions right here. I wonder if I can get Desmos to graph the whole thing, though. How would I do that? I wonder if I could trick it. So this would be if I graphed the entire sine function as an inverse, but not considering it as a function, right? Because this is not a function. The blue line is not a function because it would fail the vertical line test. It's going to give me multiple outputs for one input. Then as soon as I restrict this just to be on that range from negative pi on 2 to pi on 2, just that little part of it remains. Okay, that's pretty interesting. All right. Let's look at cosine inverse. It's like the same thing we have to do with the square root function. Remember the square root function, you know, if you've got f of x equals x squared, and then the inverse of that as a function, square root of x, whoops, the x squared graph looks like this. And then if I graph the square root of x, well, if it's an inverse function, it should just flip this function on it. It should like swap the axes, but I have to only take half of it. I have to restrict its range to ensure that it would still indeed be a function. So it's the same idea. It's just that with these trig functions, it looks a lot more extreme because of the shape of the trig functions. There's a, you know, when you only restrict to a small range like that, because you have to, it ends up, you know, you take away like all of the graph pretty much, except for that one little piece of it. So cosine inverse here on a completely unrestricted range would be a cosine wave all the way up and down the vertical axis. So what would that look like? What color did I use last time? I used blue. Okay. This one does not go through 0, 0. It actually, let me see, I'm going to turn this way to help me draw this because it's kind of hard to draw. So right here, it's at 0 here, and then tell you what, I'll label the axes after I get this down. So it's going to be like, oof, like this, and etc. Right. So this would be like a whole cosine wave just going up and down instead of left to right, right? But we want to restrict this function's range from 0. So from 0, so along here at t equals, well, I'm not using t, sorry, 0 to pi. Where is pi though? Hang on, before I say it's not there, where is pi going to be? Well, cosine is 0 at pi on 2. That's the pi on 2 value, so pi must be right here, right through there. That's pi on 2. Sorry, that's pi. That's pi. This is pi on 2 right there. All right, so let me clean this up and actually graph the actual cosine inverse as a function. It's going to go from, it's not going through 0, 0. It's starting here, which, by the way, what is that x component? That x component is 1. And then over here, I'm going to put my negative 1, maybe more like here. And then it's going right through the middle at pi on 2, somewhere there. So it's going like this, and then like that. I don't know. These are so hard to draw for some reason. It's hard to draw them sideways. And those values where it's stopping are at 0, down here, 0, and up here at pi. So that's the entire cosine inverse. Function graph right here. On its range 0 to pi. Let me show you. Let me give you a better picture. All right, so there's my little sine inverse graph. So here is x equals cosine y. Okay, there's the entire cosine wave going up and down. Not a function, right? Not a function. If I want to write it as a function, which Desmos understands that I want it as a function when I do it like this, I'm just going to take it on this little interval here. So no longer taking all the values, going from that 1, 0 up to pi as the output up here. So the y values are the range, so 0 to pi, and the domain values are the x values, -1 to 1. So they look very similar, but they're just scooted, right? Just like the original sine and cosine graphs, they look super similar to each other. They're just scooted, right? I could literally like scoot and flip this and they would overlap perfectly. Like if I, what could I do? Do I want to go this route? Yeah, I could do that. And then, this is hard to think about. Let's see what I do. Oh, no. I would go outside the function, right? To do a vertical shift. There, now they would overlap. So they're super similar. They're super similar. We're not going to be messing with transformations of the inverse trig functions, though. Or not inverse trig graphs. We're not going to be messing with transformations of them. I just want you to understand what their graphs look like and why they look like this. Okay, their ranges are extremely restricted in order for them to be functions, hence why they look like just little tiny squiggles, right? Okay. So last thing here is to just go look at the tangent inverse functions, not their graphs. We're not going to worry about that. Go. So let's discuss tangent inverse. Domain. Now this one was is different, right? This domain, the domain of tangent inverse is all real numbers. All real numbers. And its range, though, is restricted very similarly to like sine inverse, except we do not include those outer limits or outer bounds of negative pi on 2 and pi on 2. Hence why I'm using parentheses instead of brackets. All right, what I want you to be able to do here, well, I want you to just be able to evaluate stuff like this. For tangent inverse, not going to ask you to graph it, even though its graph is pretty interesting. I'll just show you real quick. It's like one period of tangent is almost like a cubic thing with vertical asymptotes. Well, those vertical asymptotes turn into horizontal asymptotes at negative pi on 2 down here and pi on 2. And its range is all the real numbers. So that means there's no restriction left to right. So it's like literally it does just take the tangent function and flip it on its side. And is it like this or this? Is it? I'd have to think about it. I didn't want to spend too much time on this. I'll just graph it. I'll just cheat real quick. Okay, oops. Yeah, of course. On the positive side, it's approaching positive, yeah, and then, okay. That would be the graph of it, which is interesting, but I'm not going to hold you accountable for knowing it or anything like that. What I am going to have you do is these over here. Evaluate each. A tangent inverse of 1. Okay, so again, hang on. What are we doing here? I'm asking a question of what angle is going to give you some relationship, like looking at the unit circles, there's some angle so that when you stack the y coordinate on top of the x coordinate, you're getting an output of 1. That's what's happening here. So you're looking for some angle on the unit circle that terminates in some coordinate point so that when you stack them on top of each other, they're just giving a 1. Why am I talking about this stacking y on x thing? Well, because tangent of t is defined as y over x, right? Whereas cosine of t is just the x value, sine of t is just the y value. Tangent of t gives you a relationship between both of them, right? It involves a ratio of y over x. And of course, what angle is going to do that? It's got to be the pi on 4, because that's where the y and the x values match. Hence, this over this will just end. So tangent inverse of 1. By the way, is 1 in the domain of tangent? Yes, because the domain is every real number. And is pi on 4 in this range? Absolutely. Pi on 4 is in that range. What about tangent inverse of square root of 3? So what should you be thinking here? You should be thinking of some angle that gives outputs probably with a square root of 3 involved, right? So that when you stack y over x, you get just the square root of 3. So I'm thinking maybe the square root of 3 over 2 comma 1 over 2, which is a pi on 6 angle, right? Or let's see, or you can just think of reference triangles as well. By the way, you can just think of reference triangles. So if I'm thinking a pi on 6 or a pi on 3, I'll just try a pi on 6 here. Pi on 6, and this side is square root of 3 and 1 and 2. Tangent is supposed to give me opposite over adjacent. So this is backwards because this is 1 over square root of 3. So it must be the pi on 3 angle, right? So it must be pi on 3. So that's it. This would equal pi on 3. Where did my red marker go? There it is. Equals pi on 3. How else could you see that from the unit circle? Well, you could say, well, if this is the pi on 3 angle, right, that orange is the pi on 3, then that x, hang on. Oh, yeah. Sorry, I just had a brain fart. The x coordinate is 1/2 and the y coordinate is square root of 3 over 2. So if you're thinking of stacking these y over x, then that math would work out, you know, square root of 3 over 2 over 1 over 2 is the same as square root of 3 over 2. That fraction arithmetic is going to work out to give you that square root of 3 that you're looking for at that angle, which is pi on 3. So that angle there is pi on 3. This is what I mean by like know how to use the unit circle. Now, maybe you're thinking like, that's crazy. I'll just use a reference triangle because it did seem easier in this case, right? Especially dealing with tangent because you have to think about stacking the y over x values. Maybe it is easier with a reference triangle. I'm kind of convincing myself as I do it that it's just easier to use a reference triangle. Okay, last little example here I want to do is tangent inverse of 20. It's not undefined, right? For cosine inverse or sine inverse, this would be undefined because their domain is just -1 to 1. The tangent inverse's domain is all of R. But how do we figure it out? Because it's not like square root of 2 over 2 or square root of 3 over 2 or square root of 3 or 1 over square root of 3 or just a 1 or a 0, whatever. It's none of those like common values that we expect to see from the unit circle. It's a 20. But you just ask the calculator. When it's not a recognizable value, you can just ask the calculator. So let me get my calculator out. I'll type 20 and then tangent inverse. And it's giving me it in degrees. So let me change it to radians. Come on, calculator. 1.52 is what I'm getting there, just by using the calculator. You notice we pretty much at this point abandoned degrees. Radians really are superior in almost every sense. Radians are superior. Maybe not like in an engineering sense or something, like in real life applications, degrees might be more, might seem easier or more appropriate, but in a mathematical sense, when you're analyzing these trig functions, radians all the way better. That's why we've pretty much abandoned degrees at this point. Okay, so that is it for 6.5. That is it for the material that's going to be covered on exam 2 coming this Wednesday. So I'm now ready for questions. We have 25 minutes for questions from the review. The review questions are in the chat somewhere. I also have them written here. And you can also ask me any questions you want from like WebAssign or the textbook or whatever. So I'll give you guys some time to find some questions. And I guess you can just either raise your hand or send a chat whenever you have a question that you'd like to ask. I'm going to go through and ask each one of you guys individually just to make sure. And like, don't be embarrassed about asking questions or anything. I guess we are being recorded, so if you make any mistake, it's recorded for like posterity's sake. But I mean, I made a huge mistake that was recorded in my 112 lecture today, so it's okay. It happens. So I'm going to go through one at a time and just ask you guys if you have any questions that you'd like to go over. So, and I'm just going to read from, oh, did I get a chat? Or is that a chat from a different meeting? No, that's Jason. Okay, never mind. Okay, so just going from left to right here. Braden, do you have any problems you want to look at for review? And the review questions, like I said, they're in the chat. If you scroll up a bit, yeah, not too far from February 15th. Or any WebAssign problems or anything. Okay. Jia Cheng, do you have any questions you'd like to go over? I see your mic is off, but I don't hear you, so. Oh, you're typing. Okay, yeah. I remember you said you had mic issues before. Okay, good so far. Caitlin?
No, I do not.
Okay. Amro, do you have any questions? Oh yeah, Ji-Cheng, you're fine. I mean, if you can, I don't really care if your mic works or not. As long as you can chat, typing out, then that's all good. Okay, Amro says he's good. Just typing something else. I'll give him a second. People are abandoning ship because I think because I'm asking. I see people leaving the meeting. That's funny. Anyways, okay, Bailey, do you have any specific questions or anything? Okay. Okay, cool. And Haley, are you good too? While Haley's thinking.
Yes, sir, I'm good.
Okay. I want to point out that those questions that I asked you to mark for review from the text. First of all, everyone knows how to get to those problems, right? They're in the ebook in WebAssign. So I hope everyone is. Let me know if you're not sure how to get to those. And they are going to be like the level of difficulty there is going to be what you're going to see on the exam. So often, like in lecture, I go a bit more intense than I expect you to replicate on the exam. So you're going to like see everything that we do in lecture and then go look at those review problems and be like, oh, this was like the easiest example he did. And that's going to be reflected on the exam. Like, I'm not going to ask you to graph like, -2 tangent inverse of x minus pi on 4 all plus pi or something crazy like that, right? Okay, if you guys are all good, then we can end early. I'm not going to start lecturing on chapter 7 stuff since we haven't taken the exam for chapter 6 yet. So you guys are good to go.